In this video, we're going to be dealing with a cylindrical barrel that is laying on its side so that's able to roll, and we are given the radius and the length as well as a fluid height that's in the barrel, and what we want to find is the pressure force that is acting on one half of the cylindrical barrel as well as one of the circular end caps. So to start, we're going to find the horizontal pressure force that's acting on one half of the cylinder. So to start, let's draw a little diagram of the kind of situation that we have going on. So we have a cylinder with a fluid height in the cylinder. So we are given that the fluid has a height h, and we are also told that there is a radius and that the cylinder has a length of L. And so to find what the pressure force is acting on one half of the cylinder, what we need to do is create kind of a panel in the middle of the cylinder that will split the cylinder in half. And the reason that we do a vertical panel is because we want the panel to be in a direction that's facing the horizontal force. And so if we have it vertical, then the pressure of the fluid is pushing onto that panel. And so this panel obviously is going to have an area. So when we want to find the total force, that can be defined as the pressure force times the differential area. And so when we're trying to find this, we're going to cut this panel into smaller sections that will give us the differential area, and then we want to sum all that up because depending on where we are getting that from, the pressure is going to be different, like different points on the panel. So we want to sum all that up, and we're going to do that with an integral. And so we are not given the area, so we need to put this differential area in terms of the heights that we're given. And so what we can do is we can take a small section here of the total height of the fluid and give that the differential height. And so that area of this, I should have drawn it, this section here, if we were to cut it into slices, is going to be the differential area times the length. And so the differential height times the length, excuse me. So the differential area is defined as length times the differential height. And then we also know the definition of pressure is, the pressure force is the rho, so the density times the gravitational acceleration times the height. And so plugging our definitions for pressure force and differential area into our integral, that gives us the integral of the density times the gravitational acceleration times the height times the length times the differential height. And now, because we have an integral, we need to set the limits for the integration. And so because we're given the fluid height, we're just going to set the limits as 0, which is at the bottom, and at h, which is at the top of the height. And because now we have another h, we need to define that this h in here are dummy variables, so we'll just give that h prime. And solving the integral, we can take the constants out. So the constants are the density, the gravitational acceleration, and the length. And that leaves us with the integral of the height times the differential height from the 0 to the height of the fluid. And solving this integral gives us the density times the gravitational acceleration times the length times the height squared over 2, solved at 0 to the height, and plugging that in, that gives us the total force on one half of the cylinder to be the density times the gravitational acceleration times the length of the cylinder times the height of the fluid divided by 2. Now that we know the total force on one half of the cylinder, we're going to find the total force on one of the circles of the cylinder, so on just this circular end here. And so to do that, we're going to redraw our diagram because now we're working with something a little different. Now we're just working with a circle, which we know has a radius r, and we know that there is a fluid at some height h. And so now that we're working with a circle, we're still going to use the idea that the total force is equal to the integral of the pressure force times the differential area. But now what we put the differential area and the pressure force in terms of is going to have to change because we're not working with a rectangular anymore, a rectangular plane anymore. We're working with a circle, so we need to put everything in terms of theta so that they are polar coordinates. And so if we defined this as theta equal to 0, we have some angle from the middle to the top of the fluid height, and this angle is theta, and so this would be theta 1. And we have another angle down here, we can call this theta 2. This is just going to be negative pi over 2, again, because now we're in polar coordinates. And so what is theta 1 up here? Well, we know that if this is the radius and this is the height of the fluid height minus the radius is going to give us this distance here. And so using our trigonometry rules, we know that theta 1 is going to be the arc sine of the height minus the radius divided by the radius. And so that gives us our definition for theta 1. Now, again, from the definition of pressure force that we used earlier, pressure force is equal to the density times the gravitational acceleration times the height. But now we need the height, the fluid height, in terms of theta as well. And so the fluid height is going to be defined as, we have the radius here, but then we have this portion up here that's going to be added to the radius. So that, using our trigonometry rules, is just going to be the radius, which is this distance here, times the sine of our angle theta. And so now that we have the pressure force in terms of the polar coordinates, we will also need the differential area in terms of the polar coordinates. So the differential area is just going to be the width of the circle times the differential height of the circle. Differential height is pretty simple, as we're just going to differentiate the height that we defined up here. And so the differential height is going to be the radius times the cosine of theta. And we can find this using our trigonometry rules. And then so the width is, if we draw another circle and we have a radius here and we have theta here, our width is also just going to be r, the radius times the cosine of theta. So this distance here. So plugging the differential height and then the width into our differential area equation, we have the differential area is the radius times cosine of theta. And I did miss one thing from the differential area. Since we differential height, since we differentiated it, it has to have the differential height at the back here. And so this would d over dh. So anyways, plugging this in would give us the radius times the cosine of theta times the radius times the cosine of theta times the differential theta. So, excuse me, sorry. this should be differential theta, d theta, not dh, because that's what we have here, is dh. So to simplify this, we can have the radius squared times the cosine of theta squared times d theta. So plugging both the pressure force equation that we have here and putting our height value up there and the equation we have here into our total force equation, that's going to give us the integral of, we'll start with the pressure force, the density, rho, times the gravitational acceleration, times the radius plus the radius sine theta, times what we have for differential area, which will be the radius squared cosine squared of theta times d theta. And our limits for this integration is going to be from our first theta 1 here. So as we defined earlier, that's going to be arc sine of the fluid height minus the radius over the radius. So we'll just put theta 1, which is equal to arc sine fluid height minus radius over the radius, up till the negative pi over 2. Distributing out constants, we're going to have the integration from theta 1 to negative pi over 2, and we have the rho times the gravitational acceleration, so the density times the gravitational acceleration, and we're going to combine these two quantities. That's going to give us r radius cubed times cosine squared of theta plus the radius cubed times sine theta times cosine squared theta d theta. Now we can distribute out this radius cubed, and that's actually going to be a constant, so we can just take it straight out of the integral. We can also take the density and the gravitational out of the integral, and that leaves us with the integral of theta 1 to negative pi over 2 times cosine squared of theta plus sine of theta times cosine squared theta d theta. And we're actually going to multiply this whole thing by 2 because we're only finding it for half, because we're only using the radius, so we're going to multiply it by 2. Just put it in there now so we don't forget it later. And we can actually separate these two integrals, and so we'll have 2 times the density times the gravitational acceleration times the radius cubed times the quantity of the first integral, which is the integral from theta 1 to negative pi over 2 times cosine squared theta d theta plus, so that's the first quantity, plus the integral from theta 1 to negative pi over 2 sine theta cosine squared theta d theta. Again, these two integral quantities are added together and then multiplied by the constants. And since this integral can be a little tricky, we're going to use Wolfram alpha, so plugging into Wolfram alpha. So when we plug that into Wolfram alpha, we get that the integral of cosine squared theta equals theta over 2 plus 1/2 sine theta cosine theta. And when we plug the integral of cosine cubed theta into Wolfram alpha, we get negative 1/3 cosine cubed theta. So plugging these integrals into this equation down here, we are going to get that the total force is equal to 2 times rho, the density, times the gravitational acceleration, times the radius cubed, times the quantity of theta over 2 plus 1/2 sine theta cosine theta evaluated from theta 1 to negative pi over 2 minus, it was plus down here, but with this negative 1/3, we'll just change it to a minus, 1/3 cosine cubed theta, also evaluated from theta 1 to negative pi over 2. So it looks a little messy, but we can simplify this. So we defined theta 1 over here as arc sine of the height minus the radius over the radius. So that means that sine of theta 1 equals the height minus the radius over the radius. And using sine of theta and the law of cosine and sine, we know that cosine of theta 1 is equal to the square root of 1 minus the sine squared of theta. And plugging sine of theta 1 in, we're going to get the square root of 1 minus the height minus the radius over the radius squared. And simplifying this further, it's going to give us the square root of the radius squared minus the quantity of the height squared minus 2 times the height times the radius minus the radius squared plus the radius squared divided by the radius squared. Simplifying this, it's going to give us the square root of the 2 radius squared cancels out. This negative turns this negative into a positive, so it gives us the square root of 2 times the height times the radius minus the height squared divided by r, the radius. So this radius should be squared up here, and so the square root of radius squared is just the radius. And so plugging this into our total force formula up here and evaluating it, we have the force equals, again, 2 times the density times the gravitational acceleration times the radius cubed. And now we start plugging our theta 1 and our sine of theta 1 and cosine of theta 1 into our evaluation. So first, negative pi over 2, plugging that in for theta, we're just going to have negative pi over 4. And then we have the sine of negative pi over 2 is just 0, so we can eliminate that term. And we're going to add, because we're going to subtract the, if we were to plug in theta 1 for this, so if we plug in theta 1 for theta up here, we have that denominator 2 and 1/2 is 1/2, and then we plug in theta 1, so that's going to be arc sine of the fluid height minus the radius divided by the radius. And then we're going to add, because you're subtracting a subtraction, if we were to plug in theta 1 for the 1/2 sine of theta cosine of theta, so we have that 1/2, and then sine of theta is just the height minus the radius over the radius, and then we have our cosine of theta 1, which is the square root of 2 times the fluid height times the radius minus the fluid height squared divided by the radius. So that's our first integral evaluated. Now we move on to our second integral. So evaluated at negative pi over 2, like I said earlier, I'm not sure if I said sine or cosine, but cosine of negative pi over 2 is equal to 0, so that term is eliminated. And then we have negative, it'll be minus, so that will turn into positive, so add 1/3, plugging in our cosine of theta 1, that's going to give us the square root of 2 times the height times the radius minus the height squared divided by the radius cubed. And that is our final evaluation. So that is our total force formula for the force on a circular end of the cylinder. And again, so this is circular end cap. And then going back to what we calculated earlier, the force on 1/2 of the cylinder is equal to the density times the gravitational acceleration times the height squared over 2 times the length. And so those are our two final formulas for force.